In the mid-20th century, researchers utilized specialized enclosures known as Skinner boxes to map the mechanics of animal learning. While early behavioral psychology relied on classical, Pavlovian conditioning, where one stimulus automatically predicts another, this passive model fails to explain how complex, voluntary behavior is acquired. Instrumental or operant conditioning requires the organism to actively operate on its environment, meaning a consequence arrives only after a specific response is made. This dynamic is formalized as a three-term contingency, a sequence that dictates how choices are made and reinforced. First, the discriminative stimulus, or SD, signals the environmental conditions. It predicts whether a specific response, R, will yield a particular outcome, O. This sequence functions as a precise computational framework, governed by mathematical laws of choice, and driven by quantifiable prediction errors firing deep within the midbrain. To understand how these computations manifest as behavior, we look at reinforcement schedules, the environmental rules determining how and when outcomes are delivered. If every action is rewarded, it is a continuous schedule. But in nature, rewards are often intermittent, following responses less than 100% of the time, in what is called partial reinforcement. A fixed interval schedule provides reinforcement for the first response made only after a set amount of time has passed. This is identical to checking for a bus that arrives every 10 minutes. The arrival is the reinforcer, but only the first check after the interval allows the opportunity to board. This creates a scalloped pattern of behavior. There is a pause immediately after the bus leaves, followed by increasingly frequent checking as the 10-minute interval nears its end. In contrast, a variable ratio schedule delivers reinforcement after an unpredictable, average number of responses, detaching the reward from a fixed timer. Because any single action could be the one that pays out, the pause disappears. The organism produces fast, steady, and relentless responding. This is why a slot machine is so seductive. The variable ratio schedule optimizes the rate of human action. Behavior under these partial schedules is also highly resistant to extinction. Once the rewards stop, an organism on a variable ratio will continue responding far longer than one on a continuous schedule. These schedules prove that organisms do not react blindly to rewards. They continuously mold the geometry of their actions to match the hidden statistical rules of their environment. When an organism is faced with multiple concurrent schedules of reinforcement, we can measure how it allocates its time and effort. The matching law states that the rate of responding will be strictly proportional to the relative frequency of reinforcement between those options. This breakdown illustrates the law using two options. Button A operates on a variable interval 2-minute schedule, and button B on a 4-minute schedule. Button A pays out twice as often, creating a 2-to-1 reward ratio. The equation predicts behavior by setting response proportion equal to reward proportion. Plugging in these values, the organism allocates 2/3 of its effort to option A. The data confirms the 67 to 33% split. The fact that behavioral output matches mathematical probabilities so perfectly suggests the brain possesses a specialized neural structure for tracking and computing relative value. These observable calculations are driven by specific associative structures that shift as a behavior is learned. In the early stages, actions are guided by expectancies, a direct association between the response and the outcome. The behavior is highly goal-directed. These associations are processed by the orbitofrontal cortex, evaluating expected rewards. With extensive overtraining, control shifts. Behavior becomes an automatic habit, where the discriminative stimulus directly evokes the response. The execution of these automatic stimulus-response habits is localized to the dorsal striatum. This transition is driven by a neurochemical signaling system that was widely misinterpreted following James Old's 1954 brain stimulation experiments. We now know that dopamine is not the brain's pleasure center. Research distinguishes between liking, the hedonic value mediated by endogenous opioids, and wanting, the motivational value mediated by dopamine. The incentive salience hypothesis shows that dopamine-depleted animals still enjoy food placed in their mouths, but they lack the motivation to work for it. Dopamine does not reward the organism with pleasure. It provides an urgent informational signal detailing how much the organism wants the outcome. Specifically, phasic dopamine acts as a reward prediction error, or RPE, signal. a measurement of the gap between what is expected and what actually occurs. Early models, like the Bush and Mosteller equation, updated associative strength based on discrete past trials. They failed to account for continuous time, computing only a weighted average of received rewards. The Sutton-Bartow temporal difference, or TD model, addresses these limitations by shifting the focus toward future events and the flow of continuous time. The TD model constantly revises its expectations, aiming to predict the value of all future rewards based on current information. When an unexpected reward is delivered to an untrained organism, dopamine neurons show a massive spike in their firing rate. However, once the organism learns to predict the reward, the dopamine neurons stop responding to the reward itself. The unexpected increment in value effectively propagates backward in time to the cue that predicts the reward, exactly as the TD model mathematically demands. If the cue occurs but the expected reward is omitted, dopamine neurons suppress their firing below baseline levels, signaling a negative prediction error. Empirical tests in the ventral striatum show that this activity strictly obeys the axiomatic criteria required for a reward prediction error system. This computation is physically executed through a three-factor rule, where synapses are permanently strengthened only when presynaptic activity, postsynaptic activity, and dopamine release occur together. By aligning these neural components with the principles of temporal difference models, we see how the brain effectively computes the future value of actions and encodes them into physical synaptic strength. Understanding the brain as a value-calculating processor reveals the mechanism behind the clinical pathology of addiction. Addictive drugs bypass environmental learning by directly hijacking the brain's reinforcement signaling mechanisms. Opiates chemically mimic endogenous opiates, artificially maximizing the liking system and producing a feeling of euphoria. Amphetamines and cocaine flood the synapse with dopamine, artificially maximizing the wanting signal and forcing the reinforcement system into an overloaded state. This creates a pathological habit, a stimulus-response association so strong it is executed relentlessly, even when the organism is consciously aware of harmful consequences. Viewed through the matching law and temporal difference models, behavior emerges as an evolutionary algorithm, endlessly calculating the expected value of the future.